Hello everyone, so today we're talking, it's chapter 3 still, part 3, and we're talking about human energy metabolism during exercise. So exercise is a stressor to the body and almost all body systems respond. If the exercise is continued daily, the body systems begin to adapt to the stress of exercise. The two body systems most involved in exercise are the nervous system and the skeletal muscular system. The nervous system is needed to activate muscle contraction, but it is in the muscle cell itself that the energetics of exercise occur. Most other body systems are simply designed to serve the needs of the muscle cell during exercise. So how do my muscles influence the amount of energy I can produce during exercise? Well, muscles constitute a significant percentage of our body weight, approximately 45% in the typical adult male and 35% in the typical adult female. However, in any given individual, these percentages may vary tremendously depending on various factors such as type and intensity of physical activity. We'll discuss the potential health and sports performance benefits associated with modifying muscle mass in later chapters, but our focus here is on energy production for exercise. The skeletal muscle cell or muscle fiber is a rather simple machine in design, but extremely complex in function. It is a tube-like structure containing filaments that can slide by one another to shorten the total muscle. The shortening of the muscle moves bones, and hence work is accomplished, be it simply the raising of a barbell as in weight training or moving the whole body as in running. Like most other machines, the muscle cell has the capability of producing work at different rates, ranging from very low levels of energy expenditure during sleep to nearly a 90-fold increase during maximal short-term anaerobic exercise. The human body possesses several different types of skeletal muscle fibers, and their primary differences are in the ability to produce energy. Various types of protein are found in muscle cells, and the production of energy is dependent on the specific type of proteins present. In general, 3 different types of skeletal muscle fiber types have been differentiated based on their rate of energy production. And Table 3.5 represents various characteristics associated with each. For comprehensive details on muscle fiber types, see the review by Schiavano and Reggiani. So, type 1 muscle fiber is also known as the slow twitch red fiber, and as this name implies, it is used for slow muscle contractions such as during rest and light aerobic physical activity. It is often referred to as the slow oxidative fiber, or SO. The characteristics associated with it, such as high mitochondria, which is our powerhouse, and myoglobin content, support its high oxidative capacity and resistance to fatigue. Use of the type 1 fiber is important during events associated with aerobic capacity and aerobic power, so endurance. The type 2A muscle fiber, also known as the fast twitch red fiber, also possesses good aerobic capacity, but not as high as the type 1 fiber. However, it may also produce energy anaerobically via the lactic acid energy system. Hence, it is often referred to as the fast oxidative glycolytic fiber, or FOG, or FOG. It also has high ATP PCR capacity. Use of the type 2A fiber is important during events associated with aerobic power and anaerobic capacity, but it fatigues sooner than the type 1 muscle fiber. The type 2B or type 2X muscle fiber, also known as the fast twitch white fiber, possesses poor aerobic capacity and is used primarily for anaerobic energy production. It is often referred to as the fast glycolytic or FG fiber. Like the type 2A fiber, it also has high ATP PCR capacity. Use of the type 2B muscle fiber is important during events associated with anaerobic power and anaerobic capacity, but it fatigues very rapidly. Most muscles contain all 3 types of muscle fibers, and all fibers are used during exercise tasks of varying intensity. However, the use of one fiber type will usually predominate, dependent on the intensity of the exercise task and the associated human energy system. Physical training can improve the efficacy of each muscle fiber type, and the benefits that accrue to each depend on the type and extent of exercise training. Moreover, the distribution of muscle fiber types will vary among different individuals due to genetic predisposition, and such differences may influence the level of success in certain sport endeavors. Wilson and others indicate that type 1 muscle fibers are found in abundance in elite endurance athletes, while type 2A and type 2B fibers are proportionally higher in elite strength and power athletes. What effect does a muscular exercise have on the metabolic rate? Well, as noted in the previous section, the REE is measured with the subject at rest in a reclining position. Any physical activity will raise metabolic activity above the REE and thus increase energy expenditure. Accounting for changes in physical activity over the day may provide a reasonable, though imprecise, estimate of the total daily energy expenditure. Very light activities such as sitting, standing, playing cards, cooking, and typing all increase energy output above the REE, but we normally do not think of them as exercise. For purposes of this discussion, the exercise metabolic rate represents the increase in metabolism brought about by moderate or strenuous physical activities such as brisk walking, climbing stairs, cycling, dancing, running, and other such planned exercise activities. The EMR is known more appropriately as the thermic effect of exercise. The most important factor affecting the metabolic rate is the intensity or speed of the exercise. To move faster, your muscles must contract more rapidly, consuming proportionately more energy. Use of type 1 muscle fibers predominates during low-intensity exercise, and type 2 fibers are increasingly recruited with more intense exercises. The following represents approximate energy expenditure in calories per minute for increasing levels of exercise intensity for an average adult-sized adult male. However, for most of us, it would be impossible to sustain the higher levels of energy expenditure for long, less than a minute or so, or the highest level could be sustained for only a second or two. Although the intensity of the exercise is the most important factor affecting the magnitude of the metabolic rate, there are some other important considerations. In some activities, the increase in energy expenditure is not directly proportional to speed, for the efficiency of movement will affect caloric expenditure. Very fast walking becomes more inefficient, so the individual burns more calories per mile walking briskly compared to more leisurely walking. A beginning swimmer wastes a lot of energy, whereas one who is more accomplished may swim with less effort, saving calories when swimming a given distance. Swimming and cycling at very high speeds exponentially increase water or air resistance, so caloric expenditure also increases exponentially. Moreover, the individual with a greater body weight will burn more calories for any given amount of work in which the body has to be moved, as in walking, jogging, or running. It simply costs more total energy to move a heavier load. So how is energy expenditure of the three human energy systems measured during exercise? As we discussed earlier in the chapter, physical activity and energy expenditure can be measured in a variety of ways, such as with the use of ergometers or accelerometers. In this section, we discuss measurement techniques to quantify energy production from the three energy human systems. Ward Smith noted that due to accurate measures of oxygen uptake and carbon dioxide, the energy contributions from aerobic metabolism are readily quantifiable, whereas the energy contribution from anaerobic metabolism is far more difficult to determine. With the ATP-PCR energy system, energy production has been measured by several procedures. One procedure involves a muscle biopsy, with subsequent analysis for ATP and PCR levels to determine use of following exercise. But the small muscle biopsy may not represent ATP-PCR use in other muscles. ATP and PCR levels may also be determined by computerized imaging procedures, a non-invasive procedure, but the exercise task must be confined to specific movements due to the nature of the imaging equipment. Thus, Lang and Burry indicate that it is difficult to obtain precise physiological or biochemical data during common explosive type exercise tests, such as short sprints. With the lactic acid energy system, laboratory techniques are also available to measure the role of the lactic acid system in exercise, primarily by measuring the concentration of lactic acid in the blood or in muscle tissues. One measure of exercise intensity is the so-called anaerobic threshold, or the that point where the metabolism is believed to shift to a greater use of the lactic acid system. This point is often termed the onset of blood lactic acid, or lactate threshold. The anaerobic threshold may also be referred to as the steady state threshold, indicating that endurance exercise may continue for a prolonged periods of if you exercise below this threshold value. Other procedures, such as the maximal accumulated oxygen deficit, are used in attempts to quantify anaerobic energy expenditure, but Nordor and others note that unlike aerobic capacity, anaerobic capacity cannot be easily quantified. The oxygen energy system is one that laboratory tests also are necessary to measure the contribution during exercise, and this is the most commonly used technique for measuring exercise intensity, and that's maximal oxygen uptake, which represents the highest amount of oxygen that an individual may consume under exercise situations. In essence, the technique consists of monitoring the oxygen uptake of the individual while the exercise intensity is increased in stages. When oxygen uptake does not increase with an increase in workload, the maximal oxygen uptake has been reached. Maximal oxygen uptake is usually expressed as VO2 max, which may be stated as liters per minute or milliliters per kilogram body weight per minute. A commonly used technique to indicate exercise intensity is to report it as a certain percentage of an individual's VO2 max, such as 50 or 75%. If blood samples are taken periodically to measure serum levels of lactic acid, the percent of VO2 max at which the steady state threshold occurs may be determined. Additionally, measurement of oxygen during recovery from exercise may be used to calculate the MAOD, as noted above, which is an indirect marker for anaerobic contributions to energy expenditure during exercise. Proper training may increase both VO2 max and the steady state threshold. So here you're seeing maximal oxygen uptake. The best way to express it is in milliliters of oxygen per kilogram of body weight per minute, or milliliters of O2 per kilogram per minute. As noted in the figure, the leaner individual has a lower VO2 max in liters, but a higher VO2 max when expressed relative to body weight. In this case, the leaner individual has a higher degree of aerobic fitness, at least as measured by VO2 max per unit body weight. Now in this diagram, the effective training upon VO2 max and the steady state threshold training increases both your VO2 max and your steady state threshold, which is the ability to work at a greater percentage of your VO2 max without producing excessive lactic acid, a causative factor in fatigue. For example, before training, the VO2 max may be 40 milliliters, while the steady state threshold is only 20 milliliters, or 50% of VO2 max. After training, VO2 max may rise to 50 milliliters, but the steady state threshold may rise to 40%, which is 80% of the VO2 max. So how can I convert the various means of expressing exercise energy expenditure into something more useful to me, such as calories per minute? A number of research studies have been conducted to determine the energy expenditure as a wide variety of sports and other physical activities. The energy costs have been reported in a variety of ways, including calories, kilojoules, oxygen uptake, and METs. The MET is a unit that represents multiples of the resting metabolic rate, which we discussed in our last chapter. These concepts are, of course, all interrelated, so an exercise can be expressed in any one of the four terms and converted into the others. For our purposes, we will express energy cost in calories per minute, based on body weight, as that appears to be the most practical method. Just in case you see the other values in another book or magazine, here's how you may simplify that conversion. We know the following approximate values. 1 calorie is equal to 4 kilojoules. 1 liter of oxygen is equal to 5 calories. And 1 MET is equal to 3.5 milliliters of O2, or oxygen, of body weight, so kilograms per minute. So amount of oxygen consumed during rest. With these calculations, these are something that you will have to determine when you go into exercise physiology or exercise testing and prescription. So it's valuable to know exactly what we're talking about here. If we look at the conversion of kilojoules to calories, these values are needed for the following calculations. If you're looking at exercise costs, at 20 kilojoules per minute. To get that calorie cost, you have to divide the kilojoules by the equivalent value for calories. So 20 kilojoules per minute divided by 4 is equal to 5 calories per minute. And if we look at conversion of oxygen uptake to calories, the exercise cost is equal to 3 liters of oxygen per minute. So to get the calorie cost, you multiply the liters of O2, which is 3, times calories per liter. So caloric cost is equal to 3 times 5. That equals 15 calories per minute. Now with conversion oxygen uptake to calories, the exercise cost is equal to 25 milliliters of O2 per kilogram of body weight per minute. You need body weight in kilograms, which is weight in pounds, divided by 2.2. For this example, 154 pounds is equal to 70 kilograms. Determine total oxygen cost by minute by multiplying body weight times oxygen cost by kilogram per minute. So 70 kilograms times 25 milliliters of O2 per kilogram per minute, and you get 1,750 milliliters of oxygen. Convert milliliters into liter. So 1,750 milliliters, that's 1.75 liters. Multiply the liters of oxygen times calories per liter. So the caloric cost is equal to 1.75 times 5. That equals 8.75 calories per minute. If you look at conversion METs to calories, the exercise cost is equal to 12 METs. So you remember at rest, you're using 1 MET. So this is 12 times that. You need body weight in kilograms. For this particular example, it's 70 kilograms. You multiply the total METs times oxygen, equivalent of 1 MET. So 12 times 3.5 milliliters of oxygen per kilogram per minute. That's 42 milliliters of oxygen per kilogram per minute. Multiply the body weight times that result. You get 70 times 42 milliliters of O2 by kilograms per minute. That's 2,940 milliliters of oxygen per minute. Convert milliliters into liters. That's 2,940 milliliters of oxygen per minute. That equals 2.94 liters of oxygen per minute. Multiply the liters of oxygen by the calories per liter. 2.94 times 5, that equals 14.7 calories per minute. We'll use this METS procedure later using a simplified formula to calculate caloric expenditure. But METS times 3.5 milliliters of oxygen per kilogram per minute times kilograms of body weight divided by 200. That would be 12 times 35 times 70 kilograms divided by 200. That equals 14.7 calories per minute. Now, energy equivalents and oxygen consumption, you have to have your calories, of course, kilojoules, and METs. This figure depicts 4 means of expressing energy expenditure during 4 levels of activity. These approximate values are for an average male of 154 pounds. If you weigh more or less, the values will increase or decrease accordingly. So, I'm going to let you solve this problem on your own. It's a sedentary, untrained 80 kilogram male running 12 minutes per mile, so at 5 miles per hour, and is consuming 3.36 liters of oxygen per minute. Assume the following: 1 calorie is equal to 4 kilojoules, 1 liter of oxygen is equal to 5 calories, and 1 MET is equal to 3.5 milliliters of oxygen per kilogram per minute. And calculate the calories per minute he is using, kilojoules per minute he's using, and the MET level at which he's exercising. So how can I tell what my metabolic rate is during exercise? The human body is basically a muscle machine designed for movement. Almost all of the other body systems serve the muscular system. The nervous system causes the muscles to contract. The digestive system supplies nutrients. The cardiovascular system delivers these nutrients along with oxygen in cooperation with the respiratory system. The endocrine system secretes hormones that affect muscle nutrition. And the excretory system removes waste products. When humans exercise, almost all body systems increase their activity to accommodate the increased energy demands of the muscle cell. In most types of sustained exercises, however, the major demand of the muscle cells is for oxygen. As noted previously, the major technique for evaluating metabolic rate is to measure the oxygen consumption of an individual during exercise. Athletes may benefit from such physiological testing. Measurements of VO2 max, maximal heart rate, and the anaerobic threshold may help in planning an optimal training program, and subsequent testing may illustrate training of testing. Such testing is becoming increasingly available at various universities and comprehensive fitness wellness centers, but very useful data, such as heart rate, may be obtained with the use of the various gadgets and apps discussed previously. Given the relationships among exercise intensity, oxygen consumption, and heart rate, the average individual may be able to get a relative approximation of the metabolic rate during exercise. A more or less linear relationship exists between exercise intensity and oxygen uptake. As the intensity level of work increases, so does the amount of oxygen consumed. The two systems primarily responsible for delivering the oxygen to the muscles are the cardiovascular and respiratory systems. There is also a fairly linear relationship between their responses and oxygen consumption. In general, maximal heart rate, or heart rate max, and VO2 max coincide at the same exercise intensity level. That's what you see here in this figure. Because the heart rate generally is linearly related to oxygen consumption, the main expression of metabolic rate. And because it is easy to measure this physiological response during exercise, either manually or at the wrist or neck pulse or with a gadget that monitors your heart rate, it may prove to be a practical guide to your metabolic rate. The higher your heart rate, the greater your metabolic rate. However, a number of factors may influence your specific heart rate response to exercise, such as the type of exercise, whether it's running versus swimming, your level of physical fitness, your gender, your age, your skill efficiency, your percentage of body fat, and a number of environmental conditions. Thus, it is difficult to predict your exact metabolic rate from your exercise heart rate. As we shall see, however, the heart rate data during exercise may be used as a basis for establishing a personal fitness program for health and weight control. So, how can I determine the energy cost of my exercise routine? As noted previously in this chapter, there are a variety of ways to determine and express the energy cost of exercise. Unless we are conducting research, most of us are interested in the caloric cost of exercise, primarily for purposes of body weight control. Various devices and smartphone applications may provide us with a good estimate, but simply knowing the metabolic cost in calories per minute for our usual physical activities may also be helpful. Bushman notes that the MET levels provided in the Compendium of Physical Activities can be a useful means to quantify the caloric expenditure of exercise. Based on the MET level provided in the compendium in Appendix B, provides an estimate of calories expended per minute for individuals of varying body weights. There's a website that you can use to find the MET level for a wide variety of physical activities as well. As noted in Chapter 1, various wearable fitness applications such as watches, wristbands, smartphones, and other such devices may provide reasonable estimates of daily energy expenditure. So what are the best types of activities to increase energy expenditure? Activities that use the large muscle groups of the body and are performed continuously usually will expend the greatest amount of calories. Intensity and duration are the two key determinants of total energy expenditure. Activities in which you may be able to exercise continuously at a fairly high intensity for a prolonged period of time will maximize your total caloric cost. Although this may encompass a wide variety of physical activities, popular modes include walking, running, swimming, biking, and aerobic dance. Walking and running are most popular because they are so practical to do. In essence, all you need is a good pair of shoes. However, as noted in Chapter 1, high-intensity interval training has become increasingly popular, particularly when time is an issue. A few general comments about some common modes of exercise would appear to be in order as well. So is swimming. Because of water resistance, swimming takes more energy to cover a given distance than does either walking or running, although the amount of energy expended depends upon what type of swim stroke you're using and the ability of the swimmer. The swimming a given distance takes about 4 times as much energy as running. For example, swimming a quarter mile is the energy equivalent of running a mile. Water aerobics and water running, which is doing aerobics or running in waist deep, chest deep, or deep water, may be effective exercise regimens to help prevent injuries due to impact. The MET values for swimming different strokes may be found in the compendium of physical activities listed under water activities. With bicycling, it takes less energy to cover a given distance in comparison to running on a level surface. The energy cost of bicycling depends on a number of factors such as body weight, the type of bicycle, heels, and body position on the bike, assuming a streamlined position to reduce air resistance. Owing to rapidly increasing air resistance at higher speeds, such as 20 miles per hour, the energy cost of bicycling increases at a much faster rate at such speeds. A detailed method for calculating energy expenditure during bicycling is presented in the article by Hagberg and Pena. In general, cycling 1 mile is approximately the energy equivalent of running 1/3 the distance. The MET values for bicycling at different speeds and under different conditions are also listed in the compendium of physical activities. Group exercise. With various types of group exercise classes, they have been popular for more than 30 years. These classes include high and low impact aerobic dance, step aerobics, Zumba, spin classes, and cardio boxing. All of these classes vary in intensity based on participant effort, but have been shown to burn up to about 10 calories per minute. Though the energy expenditure of group exercise can be comparable to individual exercise tasks such as running or cycling, the greatest benefit of group exercise might be improved exercise adherence. Burke and colleagues examined 44 studies and showed that when exercisers were given the opportunity to interact with others, as when exercising in a group, adherence was better and the exercise program was more effective. With home aerobic exercise equipment, they also provide a strenuous aerobic workout. Recent research suggests that for any given level of perceived effort, treadmill running burned the most calories. Exercising on elliptical trainers, cross-country ski machines, rowing ergometers, stair climbing apparatus also expended significant amounts of calories, more so than bicycling apparatus. Many modern pieces of exercise equipment are electronically equipped with small computers to calculate approximate energy cost as calories per minute and total caloric cost of the exercise. However, as noted above, research shows that exercise adherence is better when there is contact with fellow exercisers, as in group exercise settings. With resistance training or weight training, they may be an effective way to expend energy, but it is not as effective as aerobic types of exercise. For example, Bloomer compared energy expenditure during resistance training with free watt squatting at 70% maximal effort to aerobic training, such as cycling at 70% VO2 max for 30 minutes. Although the heart rates were the same for both types of exercise, the cycling protocol expended 441 calories, while the squatting protocol expended only 269 calories, a 64% difference. Although this is a significant difference, Bloomer noted that the resistance exercise, if performed 4 to 5 days per week, would meet the recommendations for energy expenditure as suggested by the American College of Sports Medicine. The MET equivalents for resistance type exercises are listed in the compendium of physical activities under category conditioning exercise. One of the most enjoyable ways to increase energy expenditure is sports participation. As noted above, sports such as running, race walking, swimming, and bicycling provide opportunities to expend considerable amounts of energy, as do other sports such as soccer, basketball, handball, martial arts, singles, tennis, and others. So you want to look up those in that compendium of physical activity under, they're in a wide variety of sports. Passive and occupational energy expenditure with the advances in technology have changed the way people do their jobs. Specifically, people are spending more time sitting than ever, which has been implicated in decreased daily energy expenditure and as a contributing factor to the obesity epidemic. One way people are increasing energy expenditure at work is to sit on a physio ball instead of a desk chair, or to abandon sitting entirely and simply do their job while standing at their desk, or even walking slowly on a treadmill. In the review of 32 studies, Torbines and others concluded that active workstations could increase physical activity levels. One study reported an increased energy expenditure approximating 100 calories per hour when using a walk and work treadmill. Now that sitting itself has been identified as an independent risk factor for mortality, researchers are focusing on how to increase passive energy expenditure to combat the decrease in occupational energy expenditure and to supplement daily energy expenditure to help maintain a healthy body weight. Table 3.6 provides a classification of some common physical activities based on rate of energy expenditure. The implications of these types of exercise for weight control are discussed in later chapters. Now, walking at a slow pace is more economical than walking at a faster pace or running. Kuo and others note that walking is a pendicular motion, with the stance leg behaving as an inverted pendulum and the swing leg as a regular pendulum. Thus, the pendular motion of slow walking saves energy and reduces the metabolic cost. A good rule of thumb is that you expend about 1 calorie per kilogram of body weight per mile while walking at a speed of 2 to 3 miles per hour on a level, smooth surface. However, walking faster may increase energy expenditure exponentially. The MET level for walking or jogging 5 miles per hour is the same, 8.3 METs, at high walking speeds, above 5 miles per hour, so you may expend more energy than if you jogged at the same speed. Fast, vigorous walking, known as aerobic walking or fitness walking, can be an effective means to expend calories. However, as with other exercise activity, it takes practice to become a fast walker. Various terms, including the following, have been used to describe walking based on speed. So strolling is about 2 miles per hour. That's about a 30-minute mile. Leisure walking is about 3 miles per hour or 20 minutes per mile. Aerobic or brisk walking is at about 4 miles per hour and 15-minute mile. Power walking is about 5 miles per hour and 12 minutes per mile. Race walking, on the other hand, if you're a beginner, is at about 6 miles per hour. That's about a 10-minute mile. And then race walking elite, they can get up to about 10 miles per hour, which is a 6-minute mile. That's fast. Walking intensity can be increased in other ways: climbing stairs at home, at work, and in an athletic stadium or on step machines as one means to make walking more vigorous. Carrying loads such as backpacks or hand weights is another. You do want to be careful with carrying hand weights and walking, but it is a means for increasing expenditure. So walking leisure less than 2 miles per hour would be 2 METs, whereas climbing a hill while carrying a heavy load would be approximately 12 METs. You can calculate the caloric cost of walking at various MET levels using Appendix B. For health purposes, walking may be as good as running if you have the time. In a study comparing exercise and health benefits, Williams and Thompson noted the more runners ran and the walkers walked, the better off they were in health benefits. If the amount of energy expended was the same between the two groups, then the health benefits were comparable. But the walkers need to spend about twice the amount of time as the runners to get the same benefits. So with runners, as a general rule, the caloric cost of running a given distance does not depend on the speed. It will take you a longer time to cover the distance at a slower running speed, but the total caloric cost will be similar to that expended at a faster speed. The MET levels for running at a pace of 4 miles per hour, 8 miles per hour, and 12 miles per hour are respectively 6, 11.8, and 9, resulting is comparable calculated energy expenditures within a range of 108 to 116 calories per mile for a 70-kilogram runner. So does exercise affect my resting energy expenditure? Well, exercise not only raises the metabolic rate during exercise, but also, depending on the intensity and duration of the activity, will keep the REE elevated during the recovery period. The increase in body temperature and in the amounts of circulating hormones such as adrenaline, epinephrine, which is epinephrine, will continue to influence some cellular activity, and some other metabolic processes such as circulation and respiration will remain elevated for a limited time. This effect, which has been labeled the metabolic after effects of exercise, is calculated by monitoring the oxygen consumption for several hours during the recovery period after the exercise task. The amount of oxygen in excess of the pre-exercise REE, often called excess post-exercise oxygen consumption or EPOC, reflects the additional caloric cost of the exercise above and beyond that expended during the exercise task itself. Recent research suggests that if the exercise task is sufficiently intense, the post-exercise metabolic rate may remain elevated to burn additional calories. NAB and others reported male subjects who cycled for 45 minutes at a high-intensity level, approximately 75% of their VO2 max, experienced an elevated EPOC for nearly 14 hours, totaling about 190 calories. High-intensity interval training, or HIIT, has also been promoted as a means to elevate EPOC. Skelly and others recently evaluated oxygen consumption over a 24-hour period after subjects performed either HIIT or continuous moderate intensity training. The 20-minute HIIT exercise session consisted of 10 1-minute interval exercise bouts at 90% of maximal heart rate, with each interval interspersed with 1 minute of active recovery. The continuous moderate intensity bout involved cycling at 70% of maximal heart rate for 45 minutes. Although the total oxygen cost during HIIT exercise was lower than during the continuous exercise, the total consumption over 24 hours was similar. For individuals who are aerobically fit but have limited time to exercise for body weight control purposes, the HIIT protocol may be as effective as more prolonged moderate exercise. Resistance training may also increase the EPOC, but the increase is relatively small. For example, Haddock and Wilkin found that although a bout of resistance training increased the resting metabolic rate for 120 minutes afterwards, subjects expended only about 23 more calories above the normal resting level for that time frame. Although the metabolic after effects of exercise may be relatively modest, they may add up over time. Moreover, exercise may help mitigate the decrease in the REE often seen in individuals on very low calorie diets. So does exercise affect the thermic effect of food? Many studies have been conducted to investigate the effect of exercise on the thermic effect of food. Unfortunately, no clear answer has been found. Some studies have reported an increased TEF when subjects exercise either before or after the meal, whereas others revealed little or no effects. Some research even suggests that exercise training decreases the TEF. In more recent studies, Warwick reported that prior low-intensity exercise had no effect on the TEF of a meal containing about 560 calories. Benz and others found that exercising after consuming a high-protein meal increased TEF more so than exercising after fasting. But there were no differences in TEF when compared to a low-protein meal. So other studies have investigated differences between exercise-trained and untrained individuals relative to TEF, and although some preliminary research noted a decreased TEF in endurance-trained athletes, Tremblay and others noted that it is still unclear if training causes any significant alterations in TEF. In any case, the increases or decreases noted in the TEF due to either exercise or exercise training were minor, averaging about 5 to 9 calories for several hours. So how much energy should I consume daily? Your total daily energy expenditure, or TDEE, is the sum of your BEE, which is your basal energy expenditure, your TEF, the thermic effect of food, and your TEE, your thermic effect of exercise. And you'll see in figure 3.7 provides approximate values for the typical active individual, indicating that BEE accounts for 60 to 75% of the total daily energy expenditure. TEF represents 5 to 10%, and thermic effects of food explains about 15 to 30%. These values are approximate and may vary tremendously, particularly TEE, which may range from near 0% in totally sedentary individual to 50% or more in ultra-endurance athletes. And figure 3.17, total, you're looking at the total daily energy expenditure. 3 factors account for the total daily energy expenditure. Your basal energy expenditure accounts for 60 to 75%, as we said. The thermic effect of food, 5 to 10% and 15 to 30%, is accounted for the thermic of food effect of exercise. However, all of these percentages are variable in different individuals, with exercise being the most modifiable component in the figure. The BEE is 70%, the TEF is 10%, and the TEE is 20%. So the National Academy of Sciences, through the Institute of Medicine, has released its DRI for energy in conjunction with DRI for carbohydrate, fat, and protein. Because of possible problems in developing obesity, no RDA or UL were developed for energy. Instead, the Institute of Medicine uses the term Estimated Energy Requirement, or EER, which it defines as the dietary intake that is predicted to maintain energy balance in a healthy adult of a defined age, gender, weight, height, and level of physical activity, consistent with good health. In essence, the EER estimates your REE based on age, gender, weight, and height, and then modifies this value depending on your daily level of physical activity, which we refer to in this book as the thermic effect of exercise. To illustrate the effect that physical activity, or TEE, may have on your TDEE, the Institute of Medicine developed 4 physical activity categories, or PAL, which are presented in Table 3.7. The PAL describes the ratio of the TDEE divided by the BEE over a 24-hour period. The PAL calculated as 2,000 divided by 1,400 in Figure 3.17 is 1.43, or low active. The higher the ratio, the greater the amount of physical activity. Based on a number of doubly labeled water studies, the Institute of Medicine developed equations utilizing the physical activity quotient, or PA, described below to determine the estimated energy requirement, or EER. For males 19 years and older, the EER is 662 minus 9.53 times their age, plus, and you're going to do this equation, physical activity, so looking at whatever their activity is, and then multiplying 15.91 times weight plus 539.6 times the height. You're going to do that same calculation for the females, only notice the values are a little bit different. And so age is looking at years, weight is in kilograms, and height in meters. Physical activity is the physical activity coefficient, which is based on the PAL, based on mathematical consideration to equate energy expenditure between the various PAL categories. The PA coefficient for the sedentary category was set at 1, and the PA for the other categories adjusted accordingly. The PAs for the 4 PAL categories are presented for adults and females in Table 3.7, which we'll go over in a moment. Although there may be variances in this estimate of your EER, the estimate may provide you with a ballpark figure of your daily energy needs. Let's look at an example as depicted in Figure 3.18 of the difference that physical activity may have on the daily energy needs of a sedentary, very active adult female. Both are 20 years old, weigh 132 pounds or 60 kilograms, and are 55 inches or 1.4 meters tall. So, but if we look at this, the sedentary category, the energy expenditure in individuals in the sedentary category represent their REE, including the TEF, plus various physical activities associated with independent living, such as walking from the house or work to the car, typing, and other forms of very light activity. Levine has coined the term non-exercise activity thermogenesis for these very light activities, which represent all the energy we expend daily that is not sleeping, eating, or sports-related exercise. NEAT includes such activities as playing the piano, dancing, housework, washing the car, and similar daily physical activity. For the other 3 categories, the Institute of Medicine bases the PAL on the amount of daily physical activity that is the equivalent of walking at a rate of 3 to 4 miles per hour. A low active category, an adult male who weighs 154 pounds or 70 kilograms and who, in addition to the normal daily activities of independent living, expended the physical activity equivalent of walking 2.2 miles per day, would be in the low active category with a PAL of 1.5. For to be in the active category with a PAL of 1.75, he would need to expend the physical activity energy equivalent of walking 7 miles per day. And that concludes our discussion today. We will be going over, we have one more portion that we'll add to, and we'll finish up chapter 3. I'll talk with you soon.